Hola, buenas tardes, ¿qué tal?
Hello, good afternoon. Thank you very much, everybody, for coming along. It's great to see how interested people are on what we're doing. Just starting to spread neuroscience as it has to be in Spain too. It's a great honor to have Stanislas with us today. Stanislas is in charge of the lab that has a machine to scan the brain, and this is the most powerful machine in the world. What we are about to see with him and Mariano is living science that is moving on. And it is science history, because his last book, that is the one that we're presenting here with us, with all of us, Your Brain, is one of the great milestones of this adventure. Is about discovering how the brain works. And I would like to say thank you to Espacio Telefónica for hosting us. Thanks for having us. I would like to say thank you to Mariano, who has been a great host during these days for Stan and for all the activities of the publishing house. It has been amazing to spend a while with him. You'll be able to listen to living discussions that are happening right now, all topics that we constantly deal with, AI, for example, but also about discoverings that are quite valuable to change, to transform, and to have an influence on our education systems. I think that this is one of the many topics that emerge out of neuroscientific narrative that Stanislas and Mariano do. This is a very general topic, and it can be taken advantage of. In fact, he is an advisor of the French government to change the education systems, taking into account some discoveries that changed dramatically the idea we had about learning and about how the brain works. So I hope you enjoy all this knowledge. I give the floor to Mariano.
Bueno, gracias, Santiago. So this is a series of introductions. Like Santiago introduced me, and I'm going to introduce Stan. It's a pleasure to have you all here. It's a pleasure for me to host Stan here in Madrid. Science is about producing knowledge in a very particular way. It's also about communicating knowledge, and it's about mentorships, the way we learn science from other scientists. And Stan now is my colleague, but he was my mentor, my professor, my advisor, the person that I admired, and that eventually by osmosis, by diffusion, by copying, by inspiration, I learned a style of science which I hope I have honored. And I was, in the moment, science also is about life. I spent 3 years in Paris working with Stan. It looked like 15 years, but there were 3. And there I met my wife, so these things also happen in his laboratory, so my children and my life changed in a way that I could not foresee in the moment that I made the decision to go work with Stan. And so I have many ways that I think I could introduce him, but I thought that, I think one thing, we have many things in common. One thing is our love for experiments, for discovering things and knowledge and discovering ourselves and our brains by inquiring, by doing experiments and trying to understand what these experiments tell about ourselves. And so I thought that I would honor Stan by presenting him with an experiment. And often, I imagine, Stan, this has also happened to you many times, but many times people ask me one question which we rarely ask to ourselves, like, what is the best experiment that you've done? Like your best song, that you have created, or the best. And so and then you think about something that you never thought through a question. And when this happens, I always think of an experiment where I was not like the main player of the experiment. I was kind of in a big team where I was just playing a part, a little bit like the people that win a World Cup playing 10 minutes in the World Cup, but they won it nevertheless. So you were part of the team, and it can be very inspiring. And this was I was beginning in my first days in the lab with Stan, and Stan is going to speak about technologies, but usually when you look in the brain, there used to be a compromise. Either you got very good resolution in space, a lot of detail, a very good photography, but then things in time were kind of blurred, or the other way around. You get a very exquisite resolution in time, but with a very poor resolution in space. And we're trying to change this. And it was a bit of a technological challenge. But then Stan, because that was a way of how he thought things, thought the right experiment to make the best use of this new technology that we were developing. And Stan, who also met his wife in a laboratory, these things happen among scientists. We live for science, and so we have, every now and then we do other things, but mostly we're in the laboratory, so that that's where things happen. And he continued collaborating with his wife, Ghislaine, and Ghislaine was mostly trying to understand the brain of infants, of newborns, and trying to understand how we grow a mind. So how is the brain and the mind when we have no words to speak how we think, and then we have now tools to try to inquire about this. And the question he asked, and then I joined, and Ghislaine asked, was how do we relate to language before we actually produce language? And science, I said it's mentorship. This, of course, came from ideas of Chomsky and Chomsky from other people and so on, who had this idea that in a way language is built within the brain. And that's why it's, in a way, so easy to acquire, the miracle of language, why we acquire something which is so hard when we are 1 or 2 years of life. And so, but this was an idea, and this idea had to be tested. And now we had a technology because we could look into the brain, the stream of processing in time, and try to see how babies process information while they hear a sentence. So I'm going to tell you the experiment in 2 minutes. This is my exercise. And the way it worked is adults, like now if we were to scan your brains, you're of course activating the regions of the brain of listening and of comprehension, but you're also activating a region of the brain which produces language. And this is interesting because you're not speaking, but yet the way that you have to understand language is to produce it internally. It's a way of replication, of mirroring, and kind of imitating within the mind what we observe with the eyes or with the ears in this case. This is adults. Adults, we produce language, and we have this region called the Broca area, where information goes for producing language. And when we listen to languages, information begins in the auditory cortex and then flows in time until eventually we produce the sentences in our own minds. And the question was, can babies do something like this? And then we did the experiment, and it was like really a tour de force, because babies, they do what they do. They sleep, they do not, you know babies, right? Well, some of you. And so the result was that babies, they activated the auditory cortex, the comprehension cortex, and that this information eventually went and flowed to the regions, the Broca region of a production of language. And the amazing thing to me, I didn't have kids at that time. I was trying to be with Claire to eventually have kids, which I did at some point. But so babies at 3 months, they still need to quadruple their time to produce their first words. And yet the structure, the system, the networks, the circuits for the productions of language are not only in there, but they are articulated in time in a way that has a lot of meaning. And this is the experiments which I think are incredible, because they're fascinating from it's like Chomsky to the experiments. It has a huge theoretical implication, but I think it also has an implication on how we connect to other people. Because it tells us something about, I think that for parents, there is nothing more that you would want to know that what is your child thinking of? What are they trying? What they would like to do? What they cannot do? And often this is difficult because their minds are opaque, because they don't have words to tell us what they wish, what they do, what they think, what they try. And so I liked so much this experiment. I think it's in the essence of what Stan does. It's this mixture of a fundamental theory, of a fabulous experiment on the verge of what can be done, but also something that we can take for our lives, and that somehow has a meaning on how we communicate and how we relate to the people with whom we spend our lives. So with this, Stan, I'm incredibly honored to have you here and enjoy this, because it's going to be a magnificent concert.
Thank you. I cannot dream of a better introduction. Thank you, Mariano. This is fantastic. You know that Mariano is an incredible scientist of his own. He's also an incredible author. He's the author of The Power of Words, the latest book, and you could hear the power of words, I think, through his words this morning. So thank you, Mariano. I'm really touched. I'm going to take you today on a journey inside our brain. Some other scientists take you to galaxies. I think the brain is a galaxy of its own. It's an incredibly rich world at different scales. Instead of going through the infinitely large, we go to the infinitely small. We go inside this organ, which is only 1.5 kilo, and we're going to try to retrace the history of how we can explore it and what we have discovered. And these images are all from this recent book. I'll start with this funny image, which is from the 16th century. It's a phantasm, but we cannot help but see someone being scanned here. Someone is being put inside an alchemy oven, and what comes out of it is not brain images, but it's ideas. You can see the flow of ideas from this guy's brain, or head at least. And this is exactly the phantasm that we have today still. Could we analyze the brain and understand how it makes us think, how we have ideas, and maybe even decode the ideas that we have in mind? In this case, also the phantasm was, could we extract the bad ideas? If we have bad thoughts, or if we have maybe sins, could we take them out of the brain? So we can discuss, how far can we go with technology today? But at that time, there was just a phantasm, and it was very difficult to actually discover how the brain worked. So one of the first ideas about the brain, I will skip a few steps. There's a lot more, of course, but I'll give you some of the steps. But one of the steps here was understanding that thought came from the brain, but actually the metaphor for a very long time was hydraulic machines. And the idea was that since the only machines that were around were, for instance, to open the doors of the temples in Greek times or in Egyptian times were hydraulic mechanisms, well, the brain had to be some kind of hydraulic or pneumatic machine. And this was the thought of Hippocrates, that there were humors, that were fluids, that were creating our emotions. And it led to this image, which was already still in the Middle Ages. This is from 1503, the ventricular theory. Gallen discovered that indeed there was water in the brain, there were ventricles, and you can see the 3 ventricles here, and the idea was that the flow of water would create pressure and create our thoughts. We know now this is not right, but there is some ideas that are not so bad here. So you can see the wires coming and taking the flow of information from the different senses, and the first ventricle is called sensus communis. It's the common sense. The idea was that there is something that puts together the senses, and what comes from the ears, from the eyes, and so on informs us about the external world, and then we can cogitate in the middle. This is cogitation, and then memory at the back. Well, of course, this was not quite right, and it took a lot more of data to finally discover that what was going on was in the cortex. This is one of the most beautiful images of the brain, comes from the work of Vesalius. This was published 1543, so 40 years later. People started to dissect cadavers. You can see, in fact, this is a real drawing of a dissection, and they discovered the complexities of the brain, the circumvolutions, and understood somehow that thoughts had to come from this soft organ. But they still had no idea how it could be. This problem of the relation of mind to matter, how would it be possible that ideas would relate to the matter of the brain, became so difficult that people like Descartes, for instance, renounced and decided that human thoughts, at least, had to be separate from the brain. Much later, we are moving to the 19th century. We finally reach some notion of how the brain is organized for different functions. One which is based on empirical data. This is the actual brain that you can still see in a museum in Paris. That is the brain of the patient by Paul Broca. Mariano mentioned Broca's area. You can see Broca's area. Here's this hole here. Can you see it? You can also see it in the slices here. And Paul Broca had a patient that was no longer able to articulate language, and his name was Le Borgne, but he was nicknamed Tantan because the only thing he would say is tan. Tan, 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 tan. He was trying to speak, but the only thing that came out was tan, 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 tan. And so after the patient died, for other reasons, it could see that there was this lesion in the inferior frontal region. This was nicknamed Broca's area. Broca understood that there were specific regions that were related to language. Not just one, there are many others. We'll see them later. And he understood that the left hemisphere was special, and that therefore there was specialization. There was something to be dissected about the brain. When I started my career 35 years ago, this was the source of data. There was no brain imaging. The source of data was brain lesions and the analysis of how lesions would lead to deficits, which were the deficits depending on the site of the lesion. Fast forward a few more years, and this is a very special image for me because I still remember the day I opened the journal. This was in Science, and there was another paper in Nature. You open them and you see these pictures of the active brain. For the first time, it was possible to map circuits of the brain in a living person and with identifying where is the activity as a function of what the person is doing. So this is the work of Mike Posner, Marcus Raichl, Steve Peterson and colleagues. It was a revolution. It was so-called positron emission tomography at the time. I'll just give you an idea of how this was done. It's not easy at all. You had to have a special camera that would detect radioactivity all around the head. And the person would lie in the scanner, waiting, and then in the basement, you would synthesize radioactivity with a short living period, typically oxygen 15, which you can put in the form of H2O with oxygen 15 instead of oxygen 16. It's radioactive. You rush in the corridor with a syringe. You inject it, small dose, unfortunately, in the patient or in the subject, a volunteer, and you can see where the radioactivity goes. And it goes where the brain works. And here the clever idea was to make different types of tasks inside the scanner at different times. And you can see that when the patient is hearing, or the subject is hearing, this is on the top left here, you can see this superior temporal activation. It's really fuzzy, but it was in the right place, auditory areas. If you read words, it starts in the occipital cortex. And very interestingly, as Mariano said, if you listen to words, you also get a little bit of activity in Broca's area. I hope you can see it here in the little spot in green. But you get a lot of activity in Broca's area if you generate words, if you produce words that are appropriate to the input that you're receiving. So this was the very first beginning of what we call functional mapping. We began to understand which areas are actually doing the job. But it was extraordinary that this was in a living person without any sort of consequences of this small injection of radioactivity. Of course, it was still not very nice to have to depend on a synchrotron in the basement and special chemists to create the molecule that you would inject. We still worked with that even when Mariano was in the lab. This was still the technique that his wife Claire was using. But very soon there was another revolution. MRI appeared, and we were able to use just a normal biology of the brain to look at brain activity, taking advantage of the fact that there is blood flowing, that the blood has hemoglobin, and that the molecule of hemoglobin has special magnetic property. We can use MRI to just make a map of which areas are being activated. And this was so-called functional MRI, no more injections, just lie in the scanner. Any of you could do that. You come to the lab in 3 minutes, we will map the areas of your brains. And in the hands of very clever people in California, this is the work of Jack Gallant and Alexander Huth, we are able now to make incredibly refined maps of brain areas. In this map, first of all, you see the original brain location on the right, and you see the inflated brain. In the computer, we can inflate it so that it's no longer folded, it's less complicated to analyze. And then the colors indicate the activation by different kinds of words. So now you're listening to a story or a sentence, and they manage to map which types of words will preferentially activate which areas. And you see an amazing amount of specialization. Each of the colors indicate a different domain of meaning. So for instance, the dark green indicate numbers, and there are areas that care about numbers. The red indicates social words. And you can see this is one particular location. This is a single person now. No averaging, no grouping, just one person at a time. And you can see the few words that tend to activate this particular spot of the brain. There is a spot in the brain that likes social concepts: husband, wife, confessed, admitted, nephew. These are all the words that will activate this region. This is part of the social brain in red, especially in this area, which is called the temporoparietal junction. It's part of an area that we all have in the brain and that cares about the minds of others, what others think, how others behave, and so on. But you see this remarkable specialization. It's there in one brain, but it's there in all of our brains. We can see an image like this with little degree of variation, but not too much, across many different brains. So this is the state of the art. This is from a 2016 paper in Nature by these scientists from Berkeley, Alexander Huss and Jack Gallant, and it's still very much state of the art. This is some of the best work we can do. The one thing that we can do better is to go down in scale, to try to reduce the scale. And this is the purpose of this giant machine that just arrived in our lab. This is the building where I work. It's called Neurospin. It's in the south of Paris, and you can see these sinusoids in the building. The architect had this idea that each of these sinusoids should hide one brain imaging machine. And in the most powerful of these arches, there is this giant MRI. You see the monster here. It's a prototype. It arrived a few years ago, but it's just starting to work now. It's a magnetic resonance machine, so it's a magnet. It's a giant magnet with current flowing through it. It's filled with liquid helium. It's a monster of technology with supraconductors that are cold down to 1.8 Kelvin, so very, very cold. It's just to give you an idea of the frontiers of neuroscience these days. We depend very much on development of new instruments, almost like telescopes, that are telescopes of the minds. And with this machine, we hope to be able to go down to a higher resolution, very small parcels of the brain, maybe below 1 millimeter. The target is 500 microns aside, so we can really get to the specialization of different brain areas. And one thing we can do already with such magnetic fields is acquisitions such as this one. This is a very high resolution of the human brain acquired by Cyril Poupon in Neurospin. It's a single brain, but it's at the resolution of 200 microns now. And what you can see in colors is not the activity, it's the fibers, it's the anatomy, it's the connections of the brain. Now we can tell very precisely which area is talking to whom. It's still not perfect, but it's one of the best images we have of how the brain is connected. And using it, we begin to map out the circuits of the brain, where the information flows, and try to understand the successive aspects of computations. So this image was done using the small scanners that Neurospin should get better, and in vivo. This is post-mortem. You cannot tell, of course. It's just anatomy. This is post-mortem, but we will be able to do it in vivo with the new machine. MRI is not the only game in town. Mariano mentioned some of the limits of MRI. MRI is a slow machine. MRI is largely dependent, with functional MRI, on the blood flow of the brain. We're not really measuring directly brain activity. We're measuring the blood that irrigates the brain. So it's almost like if you are looking at a garden from space, you would like to see where the flowers are, but the only thing you can see is where the gardener is putting some water. And this is our view of the brain. We see where the brain has blood flow arriving, but we don't see which specific neurons are being activated. Well, this technique is different. This technique is able to look at the activity of the brain in real time. now we really look at the electromagnetic activity of the brain millisecond by millisecond. And what you see here is a combination of two techniques. There's the white helmet, which is called magnetoencephalography. We're measuring the magnetic field arising from brain tissue. And the little dots are electrodes that measure what is classically known as the electroencephalogram, the electrical activity of the brain. And each of these has relatively high resolution. We have 256 electrodes, 300 sensors. We can really capture rather precisely where the activity is coming from, but even more precisely the time at which it's coming from. And we can follow it through time. So what can we do with this technique? I want to give you one example, which is something that I worked on very early on. And in fact, I thought that I had discovered something. It turned out that someone had published a paper just 2 months before mine, so it was a bit frustrating. This is still a very funny discovery, and you see also it's a very beautiful and strong finding. The finding is called the oops effect. Sometimes we call it the oh shit effect, but let's call it the oops effect. This is when you make an error, and I'm sure you have this familiar feeling. You're typing an email, you're clicking send, and at the moment you're clicking send, I shouldn't have done this. I forgot the attachment, or there is something nasty, it's the wrong person, and you're trying to hold it, but it's too late, right? But you know you made an error. So we had that in the lab. We have people clicking, and sometimes they click on the wrong button, but they know that they are making an error. And what you see here is the brain's reaction to an error. This is the moment of the click, and this is the brain waves when there is no error, and this is the brain wave when there is an error. When there is an error, there's this giant response in the middle of the head. It's almost like, no, but it's from inside, not from outside. It's coming from the neurons in the anterior cingulate that have very strong electrical activity that signal that the brain is detecting its own errors. So, because of this nice temporal resolution, we can see it through time, and you see that it starts just before you're making the error. And it very quickly afterwards, in less than 1/10 of a second, your brain knows that you've been making an error. So this is a very interesting system because it means that you are self-monitoring. The brain is monitoring itself. This is the first trace of the sense of the self in a very precise and narrow meaning. A system that watches its own actions and is able to detect its own actions. Of course, there is a lot more to say about this system. It's a bit paradoxical, right? Because it's the same brain that makes the error, and a few milliseconds later, the same brain is able to say, I'm making an error. But so why did you make the error in the first place? You know, it's a bit stupid. The reason this is like that is because the brain has multiple regions working at the same time. And so one region may respond, and another just slightly later is comparing and saying, no, this is not what I intended to do. So there is a comparison of the action and the intention. And we think this is what is appearing here in this image. So just an example of the following through time of information and being able to decode it and to give it a meaning. Now, the trouble is that what I showed you so far is not neurons. These are neurons. These are real nerve cells. Individual cells, we have 86 billion of them in the human brain. But with our imaging tools, we're not seeing neurons. We're seeing little cubes of brains, maybe 1 millimeter aside. What we see is signal pooling over many, many neurons, maybe 100,000 in these small cubes of cortex. We need techniques that go deeper and go down to the code, which we think is carried by the activation of these nerve cells. Each can activate more or less independently of the other, and together we think that they create their thoughts. This is a beautiful image from an animal brain. We're used to having fake colors, but this is not fake colors. This is the real colors of brain tissue after a special technique which is called Brainbow, where you manage to create fluorescent colors which are randomly distributed across cells. Each cell will have a slightly different color. So this is the actual coloring of the actual brain of the rat. And you can see the complexity of the tissue. Each of these cells has dendrites and axons going all over and connecting to each other. It's very, very complex. Can we try to understand it? And even more, can we do that in living human brains? Well, the answer is a little bit yes. In some very special conditions, we can insert an electrode, and we insert this electrode inside the human brain, not of a normal person. You cannot volunteer for that. If they are volunteers, we won't take them. You only do that in cases of epilepsy. Some patients with epilepsy will be explored with electrodes to monitor the epilepsy, try to understand where it arises, and maybe go to surgery and remove the region which is responsible for the epilepsy. But as part of this exploration, we can record from neurons, and this is from the work of Rodrigo Cuyan Quiroga, wonderful scientist, who has been able to record what he called concept cells. So this is a single neuron in the human brain, and this is how the experiment goes. You insert your electrode, you don't choose where it's going, the surgeon chooses, this is where it should go. You record a random neuron in the middle temporal lobe, and you try to understand what makes it respond. So you bombard the neuron with many, many images, very, very fast, like this. Boom, boom, boom. You have maybe 200, 300 images. And you find one that makes the neuron fire. And then you try to replicate, like a good scientist. So you go on the web, you find more images, and you try to see if you can make the neuron fire again. And by doing this, what they found here is a Luke Skywalker neuron. I think you know about Luke Skywalker. If you know about Luke Skywalker from the Star Wars series, then you probably have many Luke Skywalker neurons, such as this one here. This neuron, if you can see the little bars, these are little bars here, these are the spikes, the so-called action potentials. You can see many, many spikes for all of the top images there when Luke Skywalker is presented. But note that Luke Skywalker can be a picture of Luke Skywalker at different ages. It can be the name Luke Skywalker, spoken or written. And if you look carefully, there is one more character that makes the neuron fire. Can you see it? It's Yoda. So it's a rather funny finding, and that's it, then you remove the electrode and you cannot find the same neuron again. So that's the data. The data suggests that there are concept cells that are so abstract in the brain that they will react regardless of the modality of presentation, whether it's a word, whether it's a picture, whether you just think, whether you remember about the movie. This has been done in some experiments. And in this case, we don't really know if the concept is Luke Skywalker, and maybe Yoda makes you think of Luke Skywalker, or maybe the concept is the Jedi, and it's a broader concept. But what is very clear is that there are concept cells in the brain. There are individual neurons that care about particular concepts, and probably every single concept that you have when you hear my words is related not to one cell, but to probably thousands or millions of cells that create a collective code for the meaning. By the way, I wrote this book. This book has my brain in it. So for me, it's very special because I look at my brain. In my office, there's a printout of my brain, 3D brain. So it's like Hamlet, you look. But I wrote this also because I thought you as a reader, you think about your own brain when you see this. This is going on inside your brain at the moment. So because I'm telling you so much about Luke Skywalker, there are all these cells that are firing right now that say Luke Skywalker, and that tell you the meaning of it. So this is occurring inside your brain right now. This is really, I think, what's exciting about neuroscience. It's not about galaxies out there. It's about the galaxy that's going on inside each of you right now. It's really fascinating. I think there's a sort of recursive aspect to this. Mariano was kind enough to mention that in the lab we do experiments to try to understand how this system develops. Why we can have cells like Luke Skywalker. They must have developed, they cannot be there in the baby, but we're trying to understand how the brain comes to be through development. So what you see here is the best efforts from my wife and from a scientist called Jessica Dubois. They looked at how the brain develops, first of all in terms of its anatomy, through life. So the images in color are actually babies preterm. And the term is at the moment where it changes color, and you see the rest of the development of childhood to adulthood here. I hope you get the idea that even before birth, the brain is already extremely organized. There is a very strong genetic component to being a human, and because we are all humans in this room, we have development of a particular folding of the brain. We can recognize this at birth as a human brain, very different from a chimpanzee brain, for instance. And it's not just the folding which is organized, but the entire organization of particular areas is already visible. There are many more images I could show you, but Mariano mentioned, for instance, that language areas are already being activated in a young baby, in a 2-month-old. We did this experiment with 2-month-olds. You can already see Broca's area and the whole language system being activated when they hear speech. What we see here is that sensory areas are already organized. The colors here show you the auditory cortex, the somatosensory cortex, the visual cortex. And the reason they are in a different color is that this is showing that they are more mature. This is an index of maturity. At birth, these areas are already close, not quite, but in a few months they will be reaching their maturity, similar to adults. But because of images like this, people thought that areas of the frontal lobe or the temporal lobe were actually very immature. And they are. They are not yet quite mature. They will be slow to develop. It will take years. It's estimated that it takes 20 years, maybe 25 years, to reach a sort of peak, which we called becoming an adult. Because of that, there was a lot of neglect of the baby. People thought that the cortex of the baby was not mature enough to support cognitive functions. It was all subcortical, it was reflexes, and babies didn't have sophisticated capacities until maybe 1 year of age, where the frontal cortex would come online. And with my wife, we were able to refute this completely and discover that, in fact, babies have very sophisticated abilities from birth. And they can, for instance, perceive language, discriminate, analyze, make statistics. And that is how, in the first year of life already, they analyze their language. They're not speaking, so it's easy to neglect what they do because you don't see it from the outside. But they're already analyzing what they are getting, and to a large extent they start to understand that there are words and to begin to map these words onto meanings. So I'm showing here one of the first experiments that we did. This is actually my nephew. He must be now 30 something, 27 I think, but yeah, the whole family contributed to experiments, I'm afraid. And this is an experiment where we had babies listen to syllables to see whether they could discriminate different syllables. So the baby is listening to ba, 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 ba. I guess there's 5. Ba, 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 ba. Okay. And sometimes he hears ba, 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 ga. And there's no warning or anything. But the question is, does the brain react when there's a change in the syllable? And I hope you can see it here. So first of all, the brain habituates, and you get smaller responses when you repeat the same syllable. But then there is a massive recovery when you change the syllable. And there's in fact a frontal lobe response quite late, but that signals that the baby is probably gaining an awareness of the actual change in syllable. The baby is slow. So these responses would be much faster in an adult, but the baby is responding. And that is, I think, very characteristic of what happens in young children. If you interact with the baby, next time you interact with the baby, think that you have a fully functional brain, but slower, maybe 3 times or 4 times slower, so that the responses will take time, but after 1 second, 1 second and a half, he may become aware of something that has changed, in this case, a syllable. And there's many, many more experiments. They know about number. They know about the organization of the prosody of language. They know about other social beings. They expect people to behave according to their intentions. There's wonderful work around the baby cognition. Well, this is actually the image, one of the images that we worked on with Mariano, where you see all of the left hemisphere of the baby, and specific regions are being activated by speech, and this is Broca's area here. It's not quite the image we worked on with Mariano. He was humble enough to say that we had this image before you arrived, Mariano, but you invented the technique to change the analysis of these images and turn them into a sequence of activity. That was very clever. This is a very touching image from the lab of Rebecca Sachs. Oh, yeah, I wrote the book also because I wanted to show a panorama of research which is going on all over the world. It's like observatories of the mind. All over the world now there are big labs like Neurospin in Paris where people have developed techniques. And this is coming from MIT. It's one of the really important places for brain research. This is actually Rebecca Sachs on the left, and she's a young mother, and she took her baby to the MRI and did many experiments on her baby. And this is a touching image where they are kissing. But I use this image also to illustrate one very important point. The human brain is asking for social interactions. The human brain is really in need of language, in need of seeing other people, and this is illustrated directly in the image here, where we see in color, we see an image of the impact of speaking with your child. This is an image across many different children of how the activation changes as a function of how much children have received language inputs. So when you speak more to your child, there is many more words that he's receiving. There is a prior study that was estimating that there is a gap of 30 million words. Some kids receive 30 million words more than others at the age of 5. This is quite early on. And this is directly reflected in the amount of activation of Broca's area. The more they receive interactions, it has to be interactions, dialogues, the more you see healthy development of language areas. I say this because I think it's a very important image. The brain is already very organized at birth, but in humans, it takes 20 years to mature in a social environment. We must not forget this. It's like you have the best supercomputer. The baby is really a supercomputer. It's extracting data at a very fast rate. You need to feed this supercomputer with good data. And the data in this case is language. And this is really an important message. I think those days we have phones, cell phones, we're easily distracted. I take the train very often in Paris. I see people traveling with their kids and the kid is doing nothing because the parent is looking at the phone. There is no interaction. We are losing social interactions. This is a reminder. You know, there are sensitive periods in the brain where we need social interactions to develop these circuits. It is such an important message. There are places in the world where some kids lost 1 or even 2 years of schooling. I went to Colombia, and after 1 year and a half of start of the epidemic, they were still questioning to reopen the schools. Can you imagine the deprivation of the brain during this period? It's really a dramatic situation that we imposed on our children. And in France, I was discussing that with the public, 20% of the citizens are children. 20% of citizens are students, okay? So young students, pupils. So this is a big societal need. We need to take care of this. And I am very happy that at least in France we were able to reopen the schools very quickly. But I'm always thinking of this image as you know, the consequence of what might happen if we deprive our kids. So later on we go to school and we learn to read, and this is one thing that we've studied a lot in the brain. Learning to read changes brain activity. This is an experiment that we've been doing recently, where we were lucky enough to have the permission to scan the same children every 2 months. So you see 6 scans here, and last one 2 years later. The same child, following the same child as this is before school, and then they enter school here, and we follow them as they are being exposed to written materials, to written words. And I hope you can see that the green arrow indicates the appearance of one area that we have discovered with my colleague Laurent Cohen, which is called the visual word form area. Whenever you learn to read, this area kicks in and specializes for reading. It specializes for the shapes of words, the letters. and how the letters are organized in space. And now we can follow it. And initially you see a lot more activity, but after a little while it will concentrate inside those areas because the kids are automatizing reading. It becomes completely unconscious, and just a small circuit is specializing for reading. I think I will skip a few slides because I have too many. I was too ambitious, but maybe this gives you an image of the most recent research. This is just getting published now, but it's already in the book because I anticipated. And this is an image of what we can do with our bigger high Tesla MRIs. In this case, it's a 7 Tesla MRI, so bigger than the classical 1.5 or 3 Tesla machines that you can have in a hospital. Then what we can do is we can zoom in and make very small voxels, in this case 1.2 millimeters aside, and we can see that the reading system becomes just a set of small patches of cortex that are extremely specialized for reading, and each of them acquires the statistics of language. This is from one experiment we do in this moment. We created this stimuli on the top that you see in the scanner. They are all strings of letters, but on the right you see a French word and an English word. This is a person that could read English and French. And on the left, you see progressively deconstructing the stimulus. We shuffle the letters, we make them less frequent until you have just a string of consonants, which is completely unrelated to a real French word. And you see that in the visual cortex, it makes no difference because these are all patterns of strokes on the retina. But as you move to the front, progressively the brain will discover that this is not a possible word. The brain has internalized the statistics. The brain is a statistician. The brain has done the statistics of the strings of letters and decided that only those on the right are likely to be plausible words in English or in French. I think I'll skip over this. I wanted to tell you about mathematics, but I think it's a little bit too much. Instead, I'll just give you a flavor of where the field is going in terms of this dream, you know? Can we decipher the brain? Can we decipher it to the point of this dream that I showed you at the beginning, understanding the thoughts of another person? In this case, this is my brain. So actually, it's a backup of my brain. You scanned 20 years ago already. So that's nice to have a backup of your brain on the computer. But, you know, I don't know if I'll ever use it. But no, there is a real philosophical question. I was quite moved, actually, when I saw my brain the first time. One of the reasons to be moved was that there was a dark area in the middle of the white matter, and I was really scared. But it turned out to be an artifact of the machine. It was an old machine, and there was this artifact. But there is another moving aspect, is that the deeper thought, which is everything that I know, all of the knowledge that I have acquired is there. Everything that I am, all the decisions, you know, the capacity to decide, my biases, my voting, they are there. How does, you know, can you read them? And is it really true? I mean, how is this possible? So we started to do experiments to see how far we could go in decoding brain activity and understanding what people have in mind. And this is one of the earliest such experiments. It's based on a very simple idea. The idea is that there are maps in the brain. Whatever is on the retina maps onto the cortex, and every point in the retina maps onto a point on the cortex. So conversely, if you read the activity on a point in the cortex, almost like a painter, you could paint a little bit of the map and say, well, it's likely that there was something on the retina at this point. So you can project back from the activity to the image and try to reconstruct the image that the subject was seeing. So this is what we did here. The subject was seeing rings on the left, and he was seeing wedges that were rotating like this. And after the reconstruction, you can see the ring. It's an expanding ring like this, reconstructed from the brain of the subject. And you can see the wedge rotating. It's an image that's reconstructed from the brain of the subject. And we could show that this works with real images, but also with eyes closed. If we ask subjects, imagine a ring, or imagine the letter X, we could, to some extent, back project, measure the activity, back project it, and see that there was a little X on our picture, or that there was a little O in our picture. That was the beginning of this brain decoding. And now it can be done so much better with artificial intelligence techniques. So this is from the works of colleagues. You can see that they are now using all that we know about the specialization of different voxels in the visual cortex. For instance, we know that there are voxels that like eyes, so they put a face with eyes in the bottom. In the picture, what you see on top is what the subject was actually seeing, and on the bottom, you see the reconstruction that was made from measuring brain activity alone, without knowing what was the stimulus. You begin to see a sort of tight correspondence. It's not perfect, right? The VCR, maybe it looks like a machine or something, but this is the state of the art a few years ago. We begin to be able to take brain activity and project it back to psychological space, to what the subject was experiencing. I hope you can see the word neuron on the bottom. It was deciphered letter by letter from what the subject was seeing. And I'll finish with that. Can we do the converse? Could we write onto the brain? Could we write ideas? Well, we're not there yet, but this is from a science paper from, I think it was last year, 2 years ago, from Peter Hoefsema's lab. They are writing into the cortex and writing images. It's still the same idea. The cortex, you can see the back of the brain here. The visual cortex is a map. It's a map of the visual world. So what they did here is they put little chips that go inside the cortex. And in each site of the cortex, they started first by recording. So you see the green dots here. Each green dot is one electrode. And they mapped precisely where it responds on the original map of the screen here. So the monkey fixates on the blue dot in the middle. And each of the green dots is one point where an electrode likes to respond. And then they stimulate. And so what they do here is they take the dots in red and they stimulate them with a little electrical current. And in this way, they paint, with 16 electrodes, they paint, as you can see, a letter O. Okay? And the monkey is in darkness. There is no image. There's just the stimulation of a little bit of the cortex. And the monkey makes a saccade with his eyes to the letter O. Okay? And if you stimulate a T, I will go to the T. So the monkey has seen something which never existed. There was never any photon in this image. It's an artificial image that was painted on its brain. And it shows that something that people are searching now, we are beginning to have a two-way interface with the brain. We can read from it, and we can begin to write onto it. This is a little bit scary, but that's why I'm showing it, because I think we should have a debate about these techniques. You know, they begin to exist. They will exist. For instance, Elon Musk, you have heard with the Neuralink company, is pushing very hard these sort of techniques. Well, in his hands, maybe it's a bit crazy, I'm not sure. But in many hands like this, the goal is clinic. The goal is to recover vision. This is an incredible device for the blind. If you stimulate the cortex, you can recover vision, even in a person who is blind, maybe has completely degenerate retina, because you're going directly into the cortex. If you go to the exhibit on the 4th floor, like we just were an hour ago, you'll see a Parkinsonian patient trembling like this dramatically, with essential tremor, and you stimulate deep in the brain and you manage to stop completely the tremor. This is already existing in tens of thousands of patients throughout the planet. It's a very effective technique to compensate, not to cure, but to compensate for the symptoms of Parkinsonism and other related diseases. So we can be scared, you know, this should be checked, this should be controlled, but I would say that in 99% of the labs throughout the world, the goal is to alleviate some of the suffering which exists when you have neurological diseases. And neurological diseases, they concern essentially all of us in this room. One day or another, one of you will have a severe depression, or will have Parkinson's, or will have Alzheimer's. If you go beyond 80 or 90, it's very likely. Unfortunately, there is a good chance that we go through one of these things. These techniques may help us one day to restore the help of the machine, to restore vision or to restore mobility. So with that, I think I'll close. This is me with more hair. This is my wife Ghislaine, who did all of the work in babies, and thank you very much for your attention. Thank you. Thank you very much. So I think we have time for questions, right? And I'll take the system for translation. Sometimes my brain understands Spanish, but not always. Who would like to ask a question? Questions? Go for it.
Yeah, there's one.
Oh, there is one. Yes.
Do you prefer in English?
In
or
English
in
is
Spanish?
fine.
Okay.
Yeah.
When you do the experiments in the lab, how is the process to choose the subjects so they are not controlled, or there are no I don't know how to say it in English.
Well, so in Neurospin, we have a database of volunteers. They have to be volunteers. Nobody is forced to go in the scanner. And by the way, in Neurospin, it's only for experiments. It's not for a clinical purpose. But we have a database of volunteers. And then in some specific experiments, we may have additional requirements, like you have to be a student. Or in this reading experiment, you have to read English and French. So we control more or less, depending on the experiments. But by and large, that's the only requirements. It means that, yes, there is a certain diversity of people, and this diversity is reflected in our images. And this is actually a pretty big problem. There is a whole architecture which is common to all humans. For instance, the reading circuit that I showed you, it's always at the same place, plus or minus 5 millimeters. So when we had coarse images, plus or minus 5 millimeters was quite okay. You know, the images were bad anyway, so we just averaged the images together. Now that we have these incredibly precise images, it begins to be a problem. We really want to have single subject data, and we're trying to find ways to normalize before we average. It's a wonderful question. Can any brain be warped onto another brain? What sort of transformation is needed to go from one brain to another? Can we see the differences when we do this warping? So it's a whole array of questions that we are working on at the moment.
Thank you very much.
Thank you. Yes.
Okay. Yeah.
Oh, yeah.
One of the interesting things that I saw is that idea that in the beginnings, when we started to develop the idea of the brain, we had this idea of being something hydraulic, and then we started thinking of something that was more mechanic, and then we started thinking of this whole deterministic idea of everything is determined. And now with the development of quantum physics and the idea of non-deterministic systems, do you think that the brain is going in that direction as well?
That's a great question. We know that the processes are not fully deterministic in the brain. For instance, there is a certain probability of releasing a molecule of neurotransmitter at the synapse. And with the very same incoming action potential, the release may or may not occur. So even at that level, and we don't have to call upon quantum mechanics, really. It's really a more thermic noise, if you want, that generates randomness in the brain. And it's a very interesting question how the brain resists this randomness, probably by averaging across many cells, pooling across events so that you have robustness. But the brain is also making use of the noise in the system, in some of its algorithms. And it's a great question, yeah. So it's a very different machine from the computers that we have. The computers, since von Neumann and the engineers that work with von Neumann, we managed to reduce the noise, make sure that every bit will not change, even once in 10 to the power 20. This is really, the system is designed to be extremely robust so that we can do calculation for a long time without error. The brain is not at all like that, so the brain is not a classical computer. The brain computes with noise and manages to compute with approximate vectors, basically, approximate populations of neurons. This was the inspiration, of course, for artificial neural networks that also have this property of resisting to noise to some extent. But I don't think we fully understood how that works, especially how we can do mathematics, calculation, symbols with a brain which is noisy. That's a very big open issue at the moment. Yes, there are several.
Gracias.
Thank you for your very clear explanation. And I wonder, what can we say? I mean, what expectations we have of linking as far as possible, or even explaining the bioelectrical activity in the brain and the thoughts that we have? Thank you.
Well, the bioelectrical activity itself is well understood. We understand quite well now the biochemical processes that generate action potentials. We understand that there are channels, molecules that go through the cell membrane and let certain ions pass through, like calcium, sodium, chloride, and we understand how these create voltages through the brain. So that part, which is really like the biochemistry of the brain, is becoming really well known. Of course, it could be a little bit different in humans. So that's an interesting ongoing question. Maybe human neurons are a little bit special, and people are working on that. But let's assume that this part is understood. What is not well understood is how we go from neuron spiking to thought. It's a major bridge, and we need intermediate points. It's not going to be just one jump like this. So I showed you one cell that likes Luke Skywalker, but we need a theory of all the intermediate cells. How does that cell respond? What are the steps before it? What are the steps after it? What is the code? All of this is really big open questions at the moment. And we need mathematics. We don't have good mathematics for those steps. In fact, it's a little bit of a paradox. We have great artificial intelligence machines, but the mathematics of how they work is not very well developed. It's just being developed right now. It's a very exciting time because we can get inspiration from machines to the brain and from the brain onto machines. But this is going on at the very moment. Thank you for your question.
No sé si usted tiene conocimiento.
I don't know if you know up to what extent these techniques, the research techniques, are being used to analyze the learning problems with kids. For example, learning kids with reading, writing, etc. So up to what extent do you think that maybe they are using these techniques to make this kind of research? Thank you.
Yes. So we do a lot of work on developmental disorders. And maybe I can show again the image of reading somewhere here. Like this one. So the circuit of reading that we begin to understand very well, I wrote a whole book on this, El Cerebro Lector. We analyzed kids that have different types of dyslexias. It's important to understand that there is multiple types of dyslexias. They are not all the same. So the research in the past has been averaging across all of these types of dyslexia, and that's probably bad. But what we've definitely seen is that this area, the visual word form area, is completely abnormal. It's abnormally activated in dyslexia. It's a very good marker of dyslexia. It may not be the cause. It's very hard to know what's the cause and the consequence in the brain, because maybe the cause was 3 years before. Maybe it was genetic. There is a well-known genetics of dyslexia. If someone has dyslexia in your family, is about a 50% chance from between two brothers, for instance. There is a 50% chance of having dyslexia if one is already dyslexic. So it's huge. There's a genetic component. So definitely, yes, we are using these techniques to analyze the circuit. Many people are doing that. And we are finding very clear deficits. The difficulty is this is a developing system. It's very hard to know what's the cause and what's the consequence of what we are seeing. And pointing to the cause is very hard. Curing is even more difficult. Curing, of course, can be based on more stimulation, better learning. That's about all we have at the moment. We have zero developmental intervention that would be addressing the real cause of dyslexia at the moment. But we are beginning to understand it.
Thank you very much.
we'll finish. Thank you, and now you can buy pueden comprar los libros de Stan.
Well, now you can buy Stan's books, and Stan can sign them. For example, Reading Brain, we have it here. So,
Thank you.
Gracias
It's a great
por
pleasure.
venir.
thanks for coming along.
Thank you.